viewers, and welcome to another video. Today we are going to tackle day 23 of Advent of Code. So let's just jump right into it. So, day 23, Ampioids. A group of Ampioids notice your fancy submarine and flag you down with such an impressive shell. One Ampioid says, surely you can help us with a question that stumped our best scientist. They go on and explain that a group of timid, stubborn Ampioids live in a nearby burrow. 4 types of Ampioids live there: amber, bronze, copper and desert. They live in a burrow that consists of a hallway and 4 side rooms. The side rooms are initially full of Ampioids and the hallway is initially empty. They give you a diagram of the situation, your puzzle input, including the location of each Ampioid, each which is occupying otherwise open space, walls and space. For example, the Ampioids like the method to organize into side rooms, that each side room contains 1 type of Ampioids. The types are A and D from left to right. Ampioids can move up, left, right, so long as they are moving into an unoccupied open space. Each type of the Ampioids requires a different amount of energy for 1 step. Ember Ampioids require 1, bronze 10, copper 100 and desert 1000. The Ampioids would like to find a way to organize the Ampioids requiring the least energy. However, they are timid and stubborn, the Ampioids have some extra rules. Ampioids will never stop in the space immediately outside of a room. They can move into a space as long as they are immediately continue moving, especially this refers to the 4 open spaces in the hallway. Ampioids would never move from the hallway into a room unless the room is their destination room and the room contains no Ampioids which do not have that room as their own destination. If an Ampioid is starting in the room and it's not their destination room, it stays in that room until it leaves the room. For example, an Ampioid will not move from the hallway into the right 3 rooms and will only move into the leftmost room if the room is empty of the other Ampioids, amber Ampioids. Once an Ampioid stops moving in the hallway, it will stay that spot until it can move into a room. That is, once an Ampioid starts moving and other Ampioids currently in the hallway are locked in the place until and will not move again until they can fully move into a room. In the above example, the Ampioids can organize in the minimum of 12,521 energy. And then they show how to do that. And I have been looking into this, and as you see, I've already typed in an answer here, and you might wonder why have you already written some code? No, I just like Tower of Hanoi games, so I have done this manually. So I copied this one out, then I had a thought, and I did 1 step, and I realized that was very long, so I did another one. And that was also too long. So here I realized that it's best not to move the actual desert ones until you can actually move them directly into their room. That will save a lot. And then I tried to move the A into their specific position as fast as possible. And that helped a lot. But I put the A's over here, and then I could move them down here. So for each of these I moved first, let's see here, first we moved the B out of the way, and then I could move the A over here, and then I moved the C into its room, and then I could move the other A over here. So that's what the first 4 here is. And then I moved the B back into its room, and then I moved the other C into its room, the other B into its room, move the D's all the way over, and then move the A's back in. and that gave me something smaller. Then I thought, okay, the A's are more limber, they can move more. So perhaps I could use that fact that they don't spend as much energy, but sadly that was even longer or even more energy. So I think this is a pretty good answer. And it might be too large, and I might need to code something up, but I will try it at least. Yes! You get a gold star! I get a gold star! Everybody gets a gold star! So I'm pretty good at those games. So, continue to number 2. As you prepare to give the endpoints your solution, you notice that the diagram they handed is actually folded up. As you unfold it, you discover an extra part of the diagram. Between the first and second lines of text, they contain Ampioid starting position. Insert the following lines. Yeah, so we have some there. So the above example now becomes, yeah. So we have a bunch more down there. The Ampioids will want to be organized into rooms similar to before. And that requires 44,000. And that's a lot of steps going back and forth. Using the initial configuration of the full diagram, what is the least energy required for organized Ampioids? So either I have to build something, or I can do as I did again and give it a big think and try to solve this. And we are back again, and I found an issue with the last one, so perhaps this will be the right solution. Let's jump in here and see. Yes! You get a gold star! I get a gold star! Everybody gets a gold star! Nice! So, what I did here was pretty simple. I copied this one over here. And then I first off checked in what is the best move I can do here in order to get started. And I realized that this first one here, if I move that as furthest away as possible, so I move this over here, then I had that one out of the way. I started by moving it up here, but I realized that that's not a good choice because I want to keep the distances shorter later on. So I moved both of these over here, like this, and then I moved both of these over here, so BC. So now I have this clear, then I can move all the D's over here. And that's the shortest thing you can do in order to get those in place. And then, when you have done that, you need to move all the B's into, or move the A down here, of course. So I moved that one down here, so that's this move. And after that, I needed to move the B's out of the way so I could get these A's up. And in order to do that, I first moved this one, and I moved it over here. So that's the best option here. And then move this one up here. So, because if I move it the other way around, I will lose a little bit. Not much, but a little bit in spacing. And then I move both the A's over, so that's 10 steps each. So those go over here, like that. And now I can move the C's down here. So both C's were moved, 700, 700. So I'll get those in here, like this. And then I was able to move this B here up here. So now I have everything stacked for myself. I move the A over here, like that. That's 7 steps, so now we are here. Now I needed to figure out what's the best way to move them down, and I realized that moving this first down here, then I have a shorter way for these two to get down here. So I started with that one, and then I realized that these have the same distance, so that would be 50 and 60, independent on which one I choose. And then I need to move the last one, which also were 60 steps over. So I got that B down there. And now I needed to figure out which one was shorter, so I realized that this one was shorter, so that would give this one a little bit less distance. So I moved them first with this one over, and then the other one over here over. And that's the full list of moves that I made. So solving things manually sometimes works. So that's an interesting one. So there will not be much code in this example because I just solved it. So I like this one. Not because of the complexity, because I didn't really learn to code anything here. Could of course build a lot of things, but yeah, it was a chill one and fun to play a game. So I put it like that. If you like this one, give it a like, share it with your friends and colleagues. If you didn't like it, give it a dislike and share it with all your friends and families as well. And if you have any comments or suggestions, leave them down in the comment section. Perhaps you built some code to solve this one. I would be very much interested to see how to solve this in a programmatic way. That could be fun as well. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.